Alright, so here's the second problem we're going to be doing today concerning um, volumes of rotated solids, and we're going to be using the disk method once again. So the first step, from just like last problem, is to graph the lines x equals y squared, x equals 1, figure out where the intersection is, and then, or the enclosed area between these two, and then rotate that area about x equals 1. So we know what y equals x squared looks like. That's just a parabola that opens up. But now we're dealing with x equals y squared, so it's actually going to be a parabola that opens to the right. And then the line x equals 1 is just the vertical line at x equals 1. So now our enclosed region is this right here, and we're going to rotate that about the same line, x equals 1, so it should look something like this. Alright, so now if we take this little portion and make it bigger over here, we've got line x equals 1. Here's our vertical axis at x equals 0. And now we've got the parabola there. And now we're going to reflect that over the line here. Now what we're going to do, once again, we're going to make a thin slice in the perpendicular direction of the axis of rotation. So we have a vertical axis of rotation here, and we're going to make a horizontal slice to make a disk, and that is the general process that we use with the disk method. So now we're going to take this and rotate it around here. Do it again, so it should look like something like a really thin disk. Alright, so this slice that we took out of here to begin with, here's our x-axis, or our y-axis. Now this slice that we took out of here is very, very thin in the y direction. There's a small increase in the y direction there, which is the height of our disk. And so we're going to call that dy. Okay, so now we know our height is going to be represented by dy, and the only other main thing we have to figure out is our radius. Alright, so the radius of our disk, if we go back to the second picture, the radius of our disk looks like it's from this line, x equals 1, out to the edge here, or out to the curve, x equals y squared. So what we need to do, so now this is our radius right here, but we need to figure out what that radius is. If we look from here, from the axis to this curve x equals y squared, that's just some distance that we're going to arbitrarily call x because it moves along in the horizontal direction. Alright, and now the distance from the axis out to the line x equals 1 is always a fixed distance of 1. So this remaining piece in here, our radius, is just going to be this big part, which is 1, and subtract the smaller part, which is x. So our radius, we're going to call 1 minus x. Now that we have r and h, we just need to figure out our bounds. Since we have dy in our as our height, that means that we need to integrate with pi. Here we have r as 1 minus x squared, and then we have height as dy. We need to integrate across values of y. Alright, and the easiest way to do that is to take our two equations, our two lines, and set them equal to each other. So if we know x equals y squared and x equals 1, then we can set up on the side here 1. We know that 1 must also equal y squared. You square root both sides. We have plus or minus 1 is equal to y. So that means that our lower bound is negative 1 and our upper bound must be positive 1. So that now that goes into our integration, and now we're ready to integrate. Except for the fact that we have dy in here is not a good thing. We need to get rid of the x's because we have dy. So we called x the distance from the axis to this curve, but we know this curve is just x equals y squared. So instead of calling this 1 minus x, we can call this same thing integral from -1 to 1 of 1 minus, really getting sloppy here, 1 second. We can all call this integral pi integral from -1 to 1 of 1 minus y squared dy. And all we did was substitute x and instead plugged in y squared over here. And now we are ready to go ahead and integrate. So the first thing before we integrate this, we have to FOIL out our integration. So we're going to write this as pi integral from, you're going to skip a step here and write this quantity squared, the 1 minus y squared, as 1 minus 2y squared plus 4y to the fourth. This is still, once again, from -1 to 1, and then with dy. Alright, and if we notice back up here, this shape is actually symmetrical from -1 to 1. So instead what we can do is we can erase this. Instead of integrating from -1 all the way to 1, we can just integrate from 0 to 1 and then double it. So it'll become 2 pi times the integral from 0 to 1 of this expression. Alright, so now the only step left is to integrate it. So to do that, I'm going to erase this part again up here. So now this becomes, this 2 pi still stays out here, out front. And now if we integrate this with respect to y now, this becomes y, -2y squared becomes -2/3 y cubed, because we increase the power by 1 and then divide by that new number. And then plus 4/5 y to the 5th. And this is all evaluated from 1 to 0. Alrighty? And the nice thing about this is now we know if we plug in 0, all these terms are 0, so that won't do us any good. So all we have to do is plug in the number 1. So I get our final answer. This just becomes 2 pi times, if we plug in 1 for y, we get 1 minus 2/3, because 1 cubed is 1, and 1 to the 5th is 1. So this becomes plus 4/5. And now to finish off, all we do is add 1, -2/3, and positive 4/5. And our least common denominator will be 15ths. So this becomes 2 pi times 15 over 15 minus, multiplied by 5, minus 10 over 15 plus 12 over 15. And that gives us, so 15 minus 10 is 5, plus 12 is 17. So we end up with 2 pi times 17 over 15, or finally 34 pi over 15. And that is the final answer.